is moving left to right from positive to negative, we have a local maximum. Does that make sense? You go up and then you come down, so it has to be a maximum. Now, let's look at what's happening in the middle here. As I move across here, my derivative is negative, and doesn't it flatten out to 0? Which means we have a critical number, don't we? So to the left of it, it's negative. To the right of it, what's it going to be? Negative still. So what happens if we have a critical number? To the left, it's negative. To the right, it's negative. What does that tell us? If it doesn't change signs, it goes from negative to negative, then there is no maximum or minimum. Does that kind of make sense or not? It's kind of like you were going down, you flattened down, then you kept going down. Well, that's not going to be the highest or lowest point. You would either have to go up, then down, or down, then up. Now, at this last point on this curve, my derivative is negative, right? And then I get to a point where my derivative is 0. That's going to be right there. So that's my critical number. To the left of it, I was negative. To the right, I was what? Positive. Okay. So at the end of this all, I labeled the green part of the graph is where I'm increasing, the red is where I'm decreasing. I have a maximum here, minimum there. No maximum in there, and then a minimum. Yay? Nay? That's okay? All right. All right, now we have another test, and this comes from the second derivative. So what does the first derivative tell you? Tangent, but as far as like positive and negative, what does that tell you? If the derivative is positive, that means you're increasing, and then if it's negative, you're decreasing. So the first derivative tells us where our function's going up and down, right? Just where the function goes up and down. The second derivative also tells us something. It tells us about what's called the concavity. So I want to look at that same graph we just looked at, okay? And I'm having the computer calculate the second derivative at each of those points. So imagine taking the derivative 2 times and then plugging in the x value. Right now, my second derivative is negative, isn't it? And then it's still negative, and still negative. And then it becomes positive right there. And then it's still positive, then it's negative, then it's positive, and it stays positive. So what the hell is the second derivative telling us? It's not telling us where it goes up and down, does it? It's something else. Concave. How do you mean concave? I mean, a smile or a frown. That's what it's all about, okay? Look at the red part of this graph. Doesn't the red part of this graph look like part of a frown? Like, like a smiley face, someone's frowning? Sad face? Did I say smiley face? Okay. Frowning. Okay, a frown, right? Someone's sad face, right? Down. And then this green part is like the left side of a smile, right? If we were looking at a smiley face, that's like the left side. And then here's like the right side of a frown. And then this looks like left side of a smile and then the right side of a smile. See that? You don't see it? If you don't, tell me. Look. That's concave up. That's concave down. All right? This would mean the second derivative is positive because it looks like a smile. This looks like a frown, right? Back to my picture. This red part looks like a frown. Now, it's not the whole frown, right? It's just part of it. But this right here is where the frown becomes part of a smiley face. And then the smiley face becomes part of a frown. And then the frown becomes part of a smiley face. Do you see that now or no? Frank, I was looking at you because you shook your head. You sure? All right. Anyone else? Now, mathematically speaking, we don't talk about smiles and frowns. It's something else. And it's not many people see it right away. Does anyone see the difference between what's happening here and what's happening over here? I mean, other than the smile and frown. I'll give you a hint, unless someone sees it. The tangent line, okay. Yeah, right here in the green, isn't my tangent line below the curve? It's below the curve, right? That tangent line is underneath that curve. But when I move it over here, isn't my tangent line above the curve? That's the true definition of concavity. Anywhere your tangent line is above the function is where you're concave down. Anywhere your tangent line is below the function, you're concave up. So if I go back to my picture over here, if I pick any point on a smile and draw a tangent line, my tangent line's below the smile, right? It's touching at one point, and every point around it should be above that. And then if I go to my frown, my tangent line is above it. I mean, it touches at one point, but the rest of the line is above it. So that's the true meaning of concavity. So I'll go back up to the definition. If a function f lies above all of its tangent lines on an interval, so the function is above the tangent, then it's concave up. So you've got your smile, and you've got your tangent lines below it, right? Function is above the tangent line. If it's the other way around, the function f lies below all of its tangents, then it's concave down. That's called an inflection point. So look at this right here. If the second derivative is positive on an interval, we say it's concave up. That's easy to remember, I think. Second derivative positive means you have a smile, right? Positive people smile, for the most part. If the second derivative is negative, then it's a frown. So negative people are always grumpy, right? They're always frowning, so you've got a frown. Anywhere that you have a place where you change concavity, it's called an inflection point. So here you can move this out of here. You can switch. Here's the first switching concavity right here. Here we're frowning, concave down, and then right there is where we make the switch. Concave up, concave up. So there's our first inflection point. Here's our second inflection point, and here's our third inflection point. Okay? Questions on that? All right, second derivative test. So what was the first derivative test? It said if you have a critical number, right? And then it switches, the first derivative switches from positive to negative, you have a what there? First derivative test. You have a local max, right? If you have the first derivative is a critical number, you have a critical number, right? First derivative changes from negative to positive, you have a what? Local min. Second derivative test is a little bit different. Check out what second derivative test says. Suppose the second derivative is continuous. All right, so you take the second derivative, it's a nice function. If the first derivative is 0 at that point, what does that mean? Graphically, first derivative being 0 means what would we have there? Flat tangent line, right? Flat tangent line. If you have a flat tangent line at a point, and the second derivative is positive, then you have to have a local minimum there. Why? So let me try and illustrate this in steps. First of all, let me give you a point. Let's say that at that point, the first derivative is 0. So I have a flat tangent line, don't I? Then the second derivative is positive, which means I have to have a smile there. Can't you see that that can only be a local minimum? Right? That makes sense how that's constructed? If you look at the other way around, oops, these are all already in here. Sorry about that. So here's a point. Let's say that the first derivative is 0 there. The second derivative is negative. I have to have a frown. That means that the function has to be, or that has to be a local max. So the second derivative is very powerful. It gives you a way to find whether or not you have a local max or min pretty quickly. The drawback to the second derivative test is that you have to take the second derivative. So sometimes taking the second derivative is hard, but it's a pretty convenient little test. Okay, that's it for that section. Let me do something here. Minimize this. Yes, this is calculus right here. We were talking about inflection point. I just want to show you something real quick. Like, why is inflection point important? Let's say that this is time and this is money. Let's say you have, well, you know what, let's not use time. Let's say number of widgets produced. And let's say this is your income. And I'm just going to pick something, cell phones or, smartphones. Let's say my company makes smartphones, and that's what the widgets are. Okay, we'll just say a widget is a smartphone. I'll switch it. Smartphone. My company makes smartphones. And we produce so many per month. All right? And we make money off of those, don't we? Let's look at a graph of the income off those cell phones. What if my graph looks like this? Okay? Would you agree that the more cell phones I make, the more money I make? I'm always making money the more I produce? Do you agree with that? If I only produce this many, then I'm only going to make that much money. If I produce this many, I'll make more, right? But there's an important point on this graph, the inflection point. Okay? The inflection point is where the smile becomes the frown. It's probably somewhere in here. And in economics, in business, this is called the point of diminishing return. What it means is that if you look at the tangent line, like let's look at a tangent line over here. That tangent line's pretty steep, isn't it? Yes? But as I move past that, my tangent line is still positive, so I'm still making money, but that tangent line is not as steep as the one before it. And as I move on, I'm still making money, but I'm not making money as fast. So that green point represents the point at which I'm making the most, the fastest. Anything past that, I'm still making money, but not as quickly. That makes sense? I'm just trying to show you an example of where the inflection point might be useful in a real-world application. You could also look at this instead of smartphones. You could look at something like horsepower and fuel octane or something like that. So you realize the higher the octane, the more horsepower you're going to get, but there's this critical place where you get the most bang for your fuel, right? Does that kind of make sense? Anything past that, yeah, you're still gaining, but it's not as fast as is at that one critical place. Not everything necessarily would. I mean, some graphs might be linear, in which case the more you put in, the more you get out. There's no point diminishing return. I don't know. Yeah, I don't know. I mean, I'm just saying every model is different in the real world. If you take something as simple as, an exponential function that looks like this, that would have no point of diminishing return because it's always smiling. There is no change in concavity there. And a lot of things grow exponentially. So not everything would have a point of diminishing return. Okay. That was just to get you kind of acquainted with the ideas here. Now what I'd like to do is I'm going to do, for the next about 25 minutes, I'm going to do some examples out of the book from this section. And then you're going to take an in-class group 30-minute quiz. It's going to be a long quiz over this, okay? So I'm going to start off with the first problem here.